Hey everybody, welcome to our last little Zoom meeting, although probably we'll do like a study thing for the final as well. So welcome to who knows what order of Zoom meetings this is. So today we're just going to do the same thing that we always do. I just want to go over the optional lab that's up right now. This lab is, sort of a culmination of everything that we've learned this semester. So if you can do this lab, then I think you're set up quite well for the exam. And then I'll also show you where to find the final exam, all the information on that, and then where to also find the study guide. All right, so let's talk about the lab first. So again, this is an optional lab. So you absolutely do not need to complete this lab, but if you do, it can either make up for a lab that you might have missed, or it'll be extra credit, and it'll count the same as a lab will. So it's quite a lot of extra credit. There's no quiz associated with this, right? It's only the lab. Alrighty, so in this lab, we're talking about paleobathymetry. So paleo means old, right? Ancient. Bathymetry, we know from exercise 1, means the shape of the seafloor or the seafloor environments. So today we're going to be talking about all of these things that we've learned from exercise 1 to exercise 10 and how to put those together to look at rocks now and figure out the ancient seafloor, what's going on. So let's actually, I forgot that I have a, if it will open, there we go, a PowerPoint. Alrighty, so this is the main job of geologists, right? We do it in a lot of different ways. But our main job is to reconstruct past environments. Reconstructing past environments helps us figure out what's safe now, what will be safe in the future, and also what might occur in the future, right? So like the more we know about past earthquakes, the more we can help better predict future earthquakes. The more we know about past climate cycles, the more we can predict future climate cycles. Right, so from 4.5 billion years ago to 570 million years ago, it's really, really hard to reconstruct what the Earth may look like, or may have looked like. And the main reason for that is we've got rocks from that time period. You know, we're standing in Boone. We're standing on rocks that are about 1 billion years ago formed, which is pretty crazy. But it's hard to reconstruct what the Earth may have looked like because we don't have a lot of fossil evidence. There's definitely not mammals cruising around in 570 million years ago. And the only animals or life that is there or semi-abundant at all are these very, very small foraminifera. And so we think that at least from about 750 to 570 million years ago, the Earth was actually covered or semi-covered, so snowball versus slush ball, right, and ice. We've got evidence of that in the different types of rocks that we find. One of those rocks is very close to Boone. It's called the Conrock Formation. And if you've ever been on the Virginia Creeper Trail or been to Mount Rogers in Virginia, you'll have seen the Conrock. You might not have known it, but you'll have seen it. And it's this very maroon looking rock. And that's evidence of snowball Earth, you know, in Western North Carolina and Southwestern Virginia. And then around 570, animal life happened, right? A more abundant animal life happened. And specifically these forams, they're called foraminifera, but we just call them forams because who has time to pronounce that more than once, basically. So these are skeletal marine organisms called forams, and they're indicators of paleobathymetry. So just like now, certain animals live in certain climates, right? So if you are walking around and you find a fish skeleton in a rock, and right now it's the desert, you think that was a little bit weird, right? But if you find a fish skeleton in a rock that is now a desert, you know intuitively, right, that at some point in time in the past, there must have been a river, a lake, or an ocean there, right? And depending on what type of fish it is, you can really narrow that down. Even if you narrow it down to ocean fish, you could also probably narrow it down to, okay, well, is this deep sea, shallow sea, warm, cold, right? You can know a lot about an animal from the environment that it lives in. So we happen to know a lot about forams because they're so abundant and they're found in a suite of different rocks. So now when we find forams, we can figure out what type of environment they used to live in. So these are the reasons why we want to use forams. There's a lot of them, and they're also really small, so they can be collected in a large number. They are really easy to identify, and they are geologically stable fossils. So what that means is they're resistant to destruction through geological time. And the reason why they're so resistant is because of how small they are. They're hard to break down. Also, this is very random, but I just found out over the weekend that Daniel Boone, when he was, in Western North Carolina, going over to Tennessee, in actually Tennessee, there were so many giant sloth fossils that he would just find them on the ground. That's insane to me. Can you imagine going there, exploring this new place and then just finding these giant fossils, these giant bones everywhere? You'd be so confused. But anyways, the reason why I was thinking about that was because I was thinking of, if you've got a large animal, large bones, they're really exciting, but they break down fairly easy, right? Because there's a lot of material. However, these smaller animals do not. So if you want, you should look up what a giant sloth looks like because they're huge. And then imagine walking through Tennessee and just finding bones everywhere of giant sloths. Okay, so we've identified forams, which are really, really helpful to help us figuring out the paleobathymetry, but we also need some more help. And so that's where stratigraphy and Wather's law comes in. So this is a busy slide, just stay with me. So the stratigraphic record is the layered of preserved fossils, sediments, and rocks that record geologic time. So stratigraphy, strata is layers of rock, right? And then stratigraphic record is that is actually, this is a stratigraphic log over here. So the stratigraphic record, I'm having a time today. The stratigraphic record is that actual record of rocks. So when you pair forams with a stratigraphic record, and then you add Wather's law, we can see how rocks in a vertical sequence change. So Wather's law is that the vertical succession of facies in a stratigraphic section, so this is the vertical succession, right, reflects lateral changes in the environment. And so that's a little bit weird to think about, but let's look at this figure right here. So let's say that, oh, sorry, I just paused the share. Hopefully it's started again. If it doesn't, please just let me know. Let's say that you're standing in this sea and you want to know what's directly underneath you. If this yellow column right here is the same as this yellow column right here, right? I've got a vertical sequence of rocks. But it's not like those rocks just are within this column, right? You can see that they extend out this way, right? So if I was to stand here and do the same sort of thing, what type of rocks would I see? I would see this lower shale, this freshwater limestone right here. I would see some basal sand, and then I'd see this pink, which I'm not totally sure, bedrock, let's say. But I wouldn't see this clay, the coal, this brackish marine shale or this marine limestone, right? So the reason why I wouldn't see, let's do a different color. The reason why I wouldn't see these top 1, 2, 3, 4, 5 units over here is because that sort of environment hasn't been at this place yet. It hasn't reached this place, right? I've got I'm standing on two different environments, the marine limestone, and then this lower shale, this freshwater, this lower shale. So it's not that these rock units do not continue, right? So we can see, if I do another little drawing, we can see that these continue, right? Do you see how those connect? Same with the basal. I'm going to change it to a white, because yellow on yellow is hard to see. These connect, right? It's just that I am missing, what kind of thing? It's just that I am missing these rocks, right? They're not there. So if I am a stratigrapher and I am taking these logs at different points across a environment, I can map out how the environment has changed. So if I have no marine limestone here, but I have marine limestone here, I can say, right, the environment from this place to this place has changed from sand to marine limestone, right? And so if I can say that about those two things, I can also say that if let's label these, 1, 2, 3, 4, 5, 6, 7. So if I can say that about these two things, I can also say, let's move that a little bit closer, that this stratigraphic log has experienced a change in environment, right? And we know it's experienced a change in environment because we've got different rocks. And different rocks, a change in rocks signifies a change in environment. So at one point it was basal sand, then it was lower shale, then we were in freshwater limestone, then there was some clay, some coal, brackish, and then marine limestone. So what this signifies is an overall transgression. And transgression means that the sea level rose. And I know that the sea level rose because of these rocks, right? I go from freshwater to saltwater. So does that make sense? How I know that if I go from freshwater limestone to saltwater limestone, it means my seawater, my ocean level must have transgressed. It must have risen. Okay, same deal for here. I know that because I don't have any marine sediments here, this area has never been underwater, under marine water, right? Because if it had been, I would see some marine limestone or some brackish to marine shale, and I don't. All right, so we can use this vertical sequence of facies to look at that. So let's look over here at this large sed column. And so we're going to use the same legend as over here, basically, right? We've got limestone, we've got some shale, we've got sandstone, we've got some more shale. Okay, so here I'm going from shale to sandstone. So that's going to signify that my sea level is regressing. It's a regression because I'm going from shale, which is a deep water environment, to sandstone, which is a beach or a river environment. Do you guys remember that from Rocks of the Seafloor? Cool. And then here I'm going from marine limestone to brackish to marine shale to sandstone. So here I am, again, having a regression. But then I go back to shale, and what does that mean? That means that I am in a transgression, that my sea level is rising again. So this is just a repetition of the sea rising, falling, rising, falling, right? Falling, rising, falling, rising, falling, rising. And then basically here we're out of the ocean is, we're out of the ocean. Does that make sense? So one more time, I'm gonna draw a little box. Oh, I don't want a red box. I mean a white box, that's what color that is. So that package from sandstone to shale is a transgression. There's another transgression. There's another one. These are a bunch of little ones through here, right? That's another transgression and another transgression. So I call it a transgression because the rocks present point to sea level rising. Okay? All right, awesome. Let's keep going. So this is what we just talked about. I got a little bit ahead of myself, too pumped about oceans rising and falling. But as a review, a transgression occurs when ocean water rises, right? So this is a transgression. And a regression occurs as ocean water recedes. Alrighty, so this is what that looks like in a transgression. So let's put a, so my water starts here. I have my 1. It slowly rises. Oh, zoom, come on. Just let me move this, please. So as my water moves, my rock changes, right? So I drew a little box, or this figure has a little box right there. Let's draw some more boxes at that exact same spot at different times. Oh, not the exact same box. Feels a little bit like I cheated. That's pretty close, right? So if I look within that box, see this pulls it out, makes it a little bit bigger. I've got old land surface, sand, siltstone or shale, and limestone. So I can look over here and see the same thing. I've got old land surface, I got a tiny little bit of sandstone, and then silt, right? And then here on timeline A, I've got old land surface and sand. Okay? So does that make sense how that looks different in strat columns? And how, as the sea level rises, so as the sea level is going this way, different rocks are deposited in that same place, right? In that same spatial area. Okay. In a regression, when water recedes, wind and water might wash sediment out to a receding ocean. So it's gonna, you see it happen at the beach all the time, right? It'll take sand out. It'll take your lunch or things that you've left too close to the water line during high tide out into the receding ocean. And this erosion erases geologic time effectively, and that causes an unconformity. So you can also think about places where there are cliffs out to the sea. Every so often, as the waves beat on those cliffs, you know, there's a rock slide or a rock fall, and that is effectively eroding or erasing geologic time. And so when you have something that erodes a unit or a sediment, it's called an unconformity. So if we go quickly back to, back to this strat column, these squiggly lines are unconformities. So squiggly lines in a strat column is how geologists denote unconformities. And you'll notice, right, that they all are starting pretty much at a regressive sequence. From shale to sandstone, that's a regression, right? From limestone to siltstone, that's a regression, okay? Again, shale to sand, regression, shale to sand, regression, okay? And so these regressions are marked by these unconformities. So there are different types of unconformities, and it just basically means that they're gaps in geologic time. And they most often occur from erosion. And then like we just talked about, we usually find unconformities on top of or really on the bottom of, well, it depends on how you look at it, I guess, but we find them within regressions. We associate them with regressions. So why? Because when the sea level is rising, it erodes the rock it's rising onto, creates this erosional surface in a gap in geologic time, and then we can uncover it during regressions. So here's sort of the sequence of how things happen. Rocks are deposited. They might become folded or deformed. The top is eroded from water or wind. So if we imagine, a bunch of water on this surface, and then after that, new sediment is laid down on top of old. Right? Geology waits for no one. Time waits for no one. So immediately, even sometimes as this is being eroded, new sediment is being laid down on top of the old. So those are unconformities. So now we've got the three types of things that we need to figure out paleobathymetry. We know about stratigraphy and unconformities. We know about forams. We know about Walther's law. So let's talk a little bit more about depth indicators with those forams, and then we'll talk about the lab specifically. So there are two types of forams. There's planktic and benthic. So remember, benthic is bottom, right? It's clay material. If you do face masks, benthic clay, you like put it on your face. I'm pretty sure it's not actually good for your face, but it's a clay material, right? So clay benthic and benthic forams live on the bottom of the ocean. Planktic, you should recognize planktic from plankton, right? And they use photosynthesis, so they need to live close to where they can, or where they can gather light. So planktic forams live on the top of the ocean, benthic live on the bottom. And within that, there are three different kinds. There are neritic, which is 150 to 200 meters depth. So max is 200 meters depth that neritic forams can live. There's bathyal, and that's 150 to 4,000. So the max depth that bathyal forams can live is at 4,000. And then there are abyssal, and that's anything below 4,000 meters. So when you are thinking about this and interpreting this, slash maybe using this in your real life if you become a geologist, or just to know in general, it's always good to know things, that when you are interpreting foram data, shells of forams can be transported from shallow environments to deeper environments, right? From turbidites, remember those underwater gravity flows, from animals, from currents, from really anything, right? So we need to keep in mind that this transportation is a function of gravity. So there's really little chance that forams being transported from, forams being transported from deep water into shallower environments. All right, so seeing an abyssal foram on the now continental shelf means that there must have been some sort of regression, right? Because it's really hard to go from 4,000 meters depth to 150 meters depth without some sort of regression, right? Without some sort of change in environment. So think about that as you are doing this. So what is this? It is this lab. So what I want you all to do is go through this review, stratigraphy and Walther's law, answer some questions. And then this is the meat of the lab. You're going to use this key code, which is also underneath the subheader charts. You're going to use this key code to finish the lab. So notice, right, all this means is I've got sea level here, And I've got different types of forams that live at different depths. Okay, so I've got lower bathyal, middle bathyal, upper middle bathyal, upper bathyal, and then neritic plankton, right? So this is going to help you fill out this table. So let me move all of these Zoom things out of my way. So you all will need to complete this table right here. Click here to download. So it's going to take you here. And so if you have the capability, I would snap your screen like that, because that's the easiest thing. So it should look like this, right? You will be able to file, download it, right? I'm just going to fill it out on here for right now. So what I want you to do is look at these samples and figure out how many of these forams are in each zone. And so you might be thinking, that sounds like a ton of work. It is, but you can save this image. Let's do it. Yeah, sure, downloads. You can save this image, and I would recommend saving it and then opening it in whatever editing software you use. And then you can use the edit and create. Or no, sorry, go back. You can use the draw to mark out, I don't really care what color, mark out the forams as you count them. Okay, so what do I mean by that? As you count them is because you're going to need to look at these samples, and for each sample, so there's 8 of them, 1, 2, 3, 4, 5, 6, 7, 8. I want you to put the number of inner neritic, the number of outer neritic, the number of upper bathyal, and so forth into the appropriate columns. And so you might be thinking, how will I do that? That is, seems like a lot of information that I don't have. That's where this is going to come in, right? You're not going to find a fossil on those sample sheets that isn't here. So I would recommend doing this in groups if you can. So one group does core sample 1, core sample 2, core sample 3, core sample, so on. And then you can, use that data together. If, counting things helps with your anxiety, then you should just do this whole thing by yourself because it's a lot of counting. So that's going to be 6A. So when we talk about question 6, 6A is the percent of forams. So it asks for the percent, but we've collected 100 forams for each sample. So the percent is just going to be the number present, right? The depth is super easy. It's going to be, hold on one second. Let's open this on another tab to make things easier. The depth is going to be here. So for sample 1, it's 25. Right? For sample 2, it's 345. And then the paleobathymetry, so record the name of the environment that the max depth represents. So to do that, you're going to need to do 6A first. Okay, so let's do the first one together. So let's go to, I'm super fancy and have 3 screens. So let's do sample 1 together. We've already, I already have this here. Yes. Okay. So I want to start over. Yes. Okay. Draw. All right. So let's figure this out. Let's focus on inner neritic first. And as a reminder, so obviously we're going to have a lot of screens going on. So as a reminder, up here is my inner neritic. This is my outer neritic, right? Inner neritic, outer neritic, upper bathyal, upper middle bathyal, lower middle bathyal, lower bathyal, and nothing in abyssal. Alrighty, so interneritic looks like these guys, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. I think I got all of the swirly guys. That's 32, right? But that's not the only interneritic fossil. I also have to look for all of these. So let's look for those guys next. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. I think I got all of those. So this is plus 32. Who knew you'd also get an Excel lesson in this? So to do an equation in Excel, you just have to do equals. So we've got 32 of the swirly guys, 32 of the other guys. And then let's do the next one. So the next interneritic is this swirly girl. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33. All right, so that's 33. If any of you have any young kids in your household, this would be great counting practice. And now we're looking for these 3, I don't know, curvy things. 1, 2, 3. Is that it? Oh, that was underwhelming. Plus 3. So all of my fossils in this, or all of my forams in sample 1 are interneritic. That 32 plus 32 plus 33 plus 3 adds up to 100. So we're good to go, right? All of our fossils are interneritic. All right, so our paleobathymetry is interneritic. Okay, does that make sense why it is interneritic? Why did I do that? I don't know why this is green. What did I do to make this green? Custom. No. Reset. Okay, it's just going to be green. It's interneritic because that's the type of fossils we have, and not only is it the type of fossils we have, it's the only fossil we have. So in sample 2, it already looks like we've got some that are trailing into the upper bathyal, right? These swirly days here, but we also have some that we recognize from the interneritic, right? So in this case, what are you going to do for your paleobathymetry? When you are thinking about paleobathymetry, you want to always record the name of the environment and max depth it represents. So interneritic, our max depth of interneritic is 50 meters, right? For question Q6C, we've got a range, right? But if our max depth is upper bathyal, then that means our max depth is 50 meters, even though we see some interneritic fossils within here. Does that make sense? The reason why it is the max depth that the paleobathymetry could be is because, again, like we said, like 10 minutes ago, it's really hard for these to travel up, right? So it's quite hard for upper bathyal forams to travel up, but it's very easy for these interneritic forams to fall down because of gravity, right? So instead of minimum depth, we always want to do max depth. Okay? All right, awesome. So that's what we do for this lab. When you are, so you'll have to download this table, fill it out in Excel, upload it again. And then this is the second thing. So this looks like, wow, this is a lot more work. But all this is just transferring the information from table 11.1 and presenting it in a different way. Okay, so here's interneritic, outer neritic, upper bathyal, upper middle bathyal, lower middle bathyal, and lower bathyal. And so here for sample 1, so let's save this image, figure 5, sure, let's open it. Let's draw on it again. And let's do a different color. So for sample 1, our greatest depth was 50 meters. Oh, my battery's running low. Oh, God. Okay, so our greatest depth was 50 meters. I can't read this at all. So what that means, and our paleobathymetry was only interneritic because we only had interneritic fossils, or forams. So you're going to color. I need something thicker than that. Yeah, let's go crazy. You're going to fill this in to the interneritic. And then your percent of planktic. This is pretty awful because I can't read this at all, but I don't want to lose my recent changes. So percent of planktic material means that percent of forams that live in the area that receives sun. So let's find planktic. Da, 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 da. Planktic and benthic. But I forgot where the line was. Oh, here we go. 150 to 200. Yeah, so note that planktic foraminifera, forams, that's why I don't pronounce the whole thing, are in the neritic zone. So when it asks for the percent of planktic, in this case, we've got 100%, right? They are all planktic material. When you start getting forams that are in the upper middle, lower bathyal zone, that's when this will change. Okay, so for sample 2, remember we saw some of those samples that are in the upper bathyal zone. Even, do we see any that are lower? Not off the top of my head. So these will have a percent of forams that are planktic and a percent that are not. And to figure out that percent, you just got to go here. Does that make sense? So there are 2 figures that you sort of have to that you fill in. Actually 3, I think. But you can do it either if you have like an editing software on your computer or online. And again, this table is here. The link to it is on this lab here. Just gotta download it and fill it in. But this information and this information that goes on these 2 things are the same. Okay, you're gonna use your table to fill out this. All right, does that make sense, everybody? Hopefully. So tomorrow I won't be available for office hours, but Wednesday I will for sure, and I can still meet at different times. I'm just not going to be available during my usual times. Okay. Alrighty. Thanks for sticking with me on this longer exam. Oh, I'm going to show you where your exam will be. And I just said longer exam, I meant longer lab. So let's look on here. I'm just going to go to 202. It's the same in 204 though. Your final exam, it's hidden right now, but it's going to be right here. It's called your final exam. I'm going to unhide this or show it, as some would say. And this is going to be your review. And then your final exam will be here. It's open note, right? It is 70 questions, so it's a marathon, right? Not a sprint. So have snacks, have water. But it'll be 70 questions and it'll be open this entire week. So from April 19th to 23rd, it'll be open the entire week. You can take it at any time. You just have a 2-hour limit once you start taking the exam. Okay, if you have problems or difficulties with images, just email me. Don't panic. I can always reopen the exam for you. But just email me with a screenshot of the problem so that I can fix it right away. Please don't email me and be like, the exam isn't working for me, because that's not very helpful as far as fixing the problem. Just screenshot to me what your computer says, and then I'll be able to fix it. All right, so once again, the final exam is going to be here. It's going to open April 19th, so next Monday. It'll be open until Friday. I'll just say it's going to open at 12 a.m. on Monday, so midnight on Monday until 11:59 on Friday, or 11:59 p.m. Open at any time, and then once you start it, it's a 2-hour limit. All right. I'm going to also show this review after we get off of here, basically. Here's the Paleobathymetry lab, right? There's this quiz is going to be hidden from you. Just don't take it if you can see it, but it should be hidden. You shouldn't even be able to see it. And if you want extra cards, these are the sample cards. They're the same information, same samples, just as a PDF instead of a picture on here. Okay. Alrighty, cool deal. See you guys later. Thanks for hanging out, and I will talk to you if you need me. Just email me. Bye. See you.
Thank you.
Bye. See you.